Hello everybody and welcome back to the channel. I have a very packed week this week, so I'm in a rush to get this one recorded, but I did a great job procrastinating by spending the last 45 minutes going online grocery shopping and micro-optimizing for every single coupon possible. So I've wasted a ton of time there. Let's go ahead and get into it. Today we'll be talking about how to build a recommendation engine. One thing this video definitely isn't going to cover are any details about AI or machine learning specific content. Want to learn more about those? Consider checking out Brilliant. Did you also think that a FANG job would be the key to solving your dating troubles? Turns out it's not, because once you start getting on some Hinge dates, you realize that the only time you ever talk is doing your morning stand-up routine or bragging about your TC. That's where Brilliant comes in. Brilliant is a platform that allows you to self-study various STEM topics like math, data science, computer science, and machine learning. If you're like me, you've probably noticed that doom scrolling TikTok every day for the last 3 years has ruined your ability to focus on anything. Brilliant's interactive lessons have kept me focused and allowed me to learn. Compared to my current daily habits of laying in bed and running through my tissue supply, I found building a daily streak on Brilliant to be far more rewarding. It's also allowed me to work on my problem-solving skills so that I can easily deduce the answers to the tough questions in my life, like how come she hasn't texted me back yet? I found that in particular, Brilliant's new LLM course has been a major enabler for me to learn about key topics in modern artificial intelligence. It allows you to get hands-on experience with real-life language models. Now, instead of boring my dates with facts about mundane systems design, I can instead impress them with how to run gradient descent on a transformer network. To try everything that Brilliant has to offer for free for 30 days, check out brilliant.org/JordanHasNoLife or click the link in the description. You'll also get 20% off an annual subscription to Premium. Alright, so I'm hoping this one won't be too long, but admittedly there are a decent amount of slides, so we can go ahead and try to get through them. Also, what do we think of that ad, hey? Look who's finally selling out and doing a great job at it. Okay, here we go. So, today we are building a recommendation engine. Now I'm going to build this thing like it could be, Amazon recommending products, YouTube recommending videos, TikTok recommending videos. I'm probably going to think of it conceptually myself as YouTube videos, so maybe it'll help you guys to do the same. But note that this type of design, in theory, could work for any of those types of services. So here is an example of a recommendation that I might get for my YouTube feed. You can look at the specific videos. Obviously, they're tailored to my particular interests and hobbies. But without further ado, let's formalize some problem requirements. So number one is going to be that we want to recommend entities. So the reason I'm using the term entity is because, again, this is a generalizable thing. An entity, if this were YouTube, would be a video. An entity, if this were Amazon, would be a product. And another thing that we want to do is make sure that if we are making recommendations, that we're not recommending entities that a given user has already seen. Cool. So like I mentioned, examples are YouTube, TikTok, and Amazon. All right, moving on. I'm not going to give any capacity estimates here just yet. I'll briefly go over where they might be relevant in a little bit. The reasoning being that, again, the types of recommendation engines that you may be building across these services are extremely different. For example, on TikTok, a user is going to watch quite a bit more videos than they would on YouTube because they're all short form. So it's not really fair to make a single capacity estimate for all of these. I'll make them where they're relevant. So what would a naive solution to a problem like this be? Well, basically, it would look something like this. We've got some app servers, right? So imagine this is YouTube, and in an app server, I would basically say, I just watched a video. That would go to my user history table. We could throw that over in Kafka, get it over in Flink, combine all that data into Parquet files, sync it into Hadoop, and then once per day, run a batch job where we look at all of the videos. We look at all of the history of a user that, what they've watched, what they've liked, what they've commented on, how long they watched it. And then we could spit out a bunch of recommendations into a user recommendation cache. And then that way, we go ahead and load it from our recommendation servers. So that's good, but there are a few fundamental issues with it, right? It means that, for starters, intraday videos will not be recommended, which is not going to be feasible. As a YouTuber, when I post a video on a Saturday, if I had 0 views for the entirety of that day, I would probably cry and stop posting. So it's important that you get intraday videos in there, and additionally, if I go through my cache, I don't want to have to wait until tomorrow in order to get an up-to-date cache. I would like it to refresh very quickly. Cool. So now I'm going to kind of outline the overall ideas that we want to keep in mind when we're making a service like this. And the biggest thing is that we want to keep our read latency as low as possible. So we want to be able to fetch recommendations for a user as fast as possible. Because whatever we do on the right path, right, however long it takes us to actually create these recommendations, at the end of the day, what we really care about is our user experience, and the user experience is dictated by how quickly they're able to fetch all of those videos that they want to watch. Cool. So perhaps this does involve some amount of caching per user, but at the same time, keep in mind that there's a trade-off here, right? A lot of that caching that we may do may actually be a front-end optimization. So if we're talking about TikTok, maybe we see, oh, you know what, we've got 5 videos left in the ones that we currently recommended. Right about now, we should start pulling in another set of potentially recommendable videos, and that way, you know, we've got this already pulled in. So in addition to the caching itself being fast, or right, like a cache of videos being easily accessible, what we also want is that the actual query to go ahead and fetch recommended entities should itself be pretty fast, right? So we need to be able to repopulate that cache quickly. So I was just mentioning this TikTok example, and on YouTube in general, there probably is no cache because, you know, you're only loading those when you first load up the page. And if you actually look at how YouTube works, every time you reload that change or reload that page, the recommended videos do actually change up a little bit. So one could assume that you are probably running the full query of, hey, get the recommended videos for this user on every single page load. Cool. So again, a lot of this could be front-end optimizations, right? It's possible that YouTube does cache all those videos, but then just randomly actually sends a subset of them to you every time you load the page. Hard to say, but I'm going to spend a lot of time focusing on this part particularly quickly, which is actually running the query to find those recommended entities. Cool. And so like I said, that involves doing as much work as possible on the right path. So we're going to have to do some caching elsewhere. Great. So the first concept that I want to cover is going to be embeddings. I did mention I'm not going to talk a lot about machine learning concepts in this video, but embeddings are pretty essential to this problem, so we do have to understand them. So basically, if I have 2 videos, for example, how do I actually determine the similarity between them? Well, I can't really just look at them frame to frame. I suppose I could, but that would require a human going through them. So we want to be able to represent these things with numbers somehow, or more specifically, with vectors. So a vector, even though I draw them as arrows on my screen here, are basically just going to be, you know, a point in space. And so an embedding is basically a vector representation of our entity. So again, a vector representation of a video or an Amazon product or something like that. So for example, if we're drawing out coders as embeddings, you can see Jordan, Jeff Dean, and Donald Knuth are very similar to one another in that vector space. But tech lead, the sham, is all the way on the other end of the coordinate plane. Cool. So the idea here is we take our video, we actually put it through an embedding model, where an embedding model just has a bunch of weights, and using those we're able to transform our video into a singular vector. So keep in mind, in reality, that vector is not going to have 2 dimensions. We have to code a lot of information here, and so it'll probably have hundreds or perhaps even thousands of dimensions. Cool. So as far as our actual embedding model goes, like we mentioned, our problem requirements here are that we want to be able to incorporate new videos into user feeds, and we want to be able to refresh our user feed as necessary. And so the embedding model itself doesn't have to be changing in real time. We could perhaps update that offline in batch. And then if we did change our embedding model, or we changed how we represent our embeddings, obviously we would have to change quite a bit on our back end to account for that. Another thing to note that I'm just going to say quickly as a caveat is that services like TikTok, for example, I believe, I was reading a little bit about them, do actually do some real-time updates of their embedding model because the features that they care about in those vectors are changing all the time. That being said, that is a concept for a different video and perhaps not even for my channel because it's just not really what I want to focus on. Cool. So in conclusion, we're actually going to basically generate these recommendations in 2 different steps via a 2-step process. So we're going to call those retrieval and ranking. So they're pretty simple for the most part. In retrieval, we fetch the last X entities that I've interacted with. So let's say for YouTube, maybe it's the last 10 videos that I've interacted with. From there, we're basically going to take each of those last 10 videos and we're going to fetch for each of them the closest 10 videos to them, right? So the last Y most similar entities. And the way that we're going to do that is using our embeddings, because embeddings are numeric, and they allow us to compute similarity between two vectors. The next step is going to be ranking. After we do all of this retrieval, we now have a bunch of candidate vectors, and we have to rank them to take the top few that are most relevant for a given user. So we can basically assign a score to all x times y of these embeddings. We can filter out all of the entities that I've seen before. So if it's YouTube, I don't want to see recommendations for videos I've already seen. And then all we're going to do is sort them by their score and return to the user. So it's possible that to some extent they might already be pre-sorted, right? For each one of these entities, maybe all of their neighbors are pre-sorted, so we don't have to do a full sort, but we'll talk about that in a little bit. Cool. So the first thing that I'm going to talk about here are our recommendation servers, right? When I want a list of videos that I want to get recommended, I reach out to the recommendation server. So it is going to be really, really nice for us. We're going to get a lot of good data locality features if we make sure that I am always sending my recommendation requests to the same server. And there's a couple reasons for that. First off, we can do quite a bit of pre-caching of the last X entities that I've seen. So, if I know that server A is always going to be handling my recommendation requests, server A can actually preload every single video that I watch as I watch it. And that way, it doesn't actually have to go to a database and fetch them every time I ask for new recommendations. Cool. And in addition to that, it can keep some details about what I did while I was watching them as well, whether I liked, whether I commented, whether I disliked, how long I was watching, details like those. Cool. And then another thing that we can do is that we can actually potentially pre-cache my interactions with all historic entities, right? So this might be a little bit storage intensive, but if a particular server knows that it's going to be handling all of my recommendation requests in the future, it could, in theory, cache every single entity that I've ever looked at, and that way it can easily blacklist entities so they make sure that they don't recommend them to me again. Cool. So again, the way that we would do this is something we've done plenty on this channel before. Use consistent hashing, so that way we know exactly which user ID is mapped to which recommendation server, and by doing so, we can actually pre-cache all of this information. I will discuss the fault tolerance of this later in this video, but for now, this is just in the overview phase of it. All right, so let's start going through our two-step process. So right now, what we're first going to talk about is step 1A, which is getting those last X entities. Like I mentioned, this is information that we want to be pre-caching on our recommendation server. So let's say that this is me, Jordan, over here. I watch a video, so I watch some Karinikov live stream highlights. That's going to flow into my entity history database, which I can shard on my user ID, so it all goes to the same partition. We then go ahead and have all of our change data captures stream into Kafka, and from there, our recommendation server can handle it. So once our recommendation server gets a specific entity ID, it can say, ooh, it would also be great. Not only do I want to pre-cache this entity, but I also want to pre-cache the vector for this entity, right? The embedding. So it can actually go over to our entity database, which can contain the embeddings for each particular entity ID, right? This is just a mapping of entity ID to embedding. And it's possible that, if certain videos are super popular, that we may constantly have servers reaching out to the entity database to get their embedding. And so for that reason, I also have an entity cache here, right? If everyone wants to see the embedding for the new Mr. Beast video, we should probably all be hitting that cache. And just use LRU, something like that, make it fast. Great. So hopefully that goes to show how all of the information pertaining to what entities I interact with flow down into that recommendation server and get cached. Now, of course, again, if each server, I do a little bit of a computation down here because we want to make sure that we're not caching too much information per user, right? So if each server handles 5 entities for 100,000 users, where each embedding for those entities is a vector of 500 floats, so that's 4 bytes per float, this basically means that that recommendation server only needs to keep 1 gigabyte of data in memory, which is really not that much. This thing probably has hundreds of gigabytes of RAM on board, and so having to store just 1 gigabyte for this process is great because it avoids an extra database call to get my last few watched entities or last few seen entities every single time that we make a request for recommended entities. Cool. So that's step 1A. Step 1B, as we mentioned, is we take all of those last entities that I've seen, let's say the last 5 videos I watched on YouTube, and we want to find all of the most similar videos on YouTube to those that I recently watched. Great, so let's go through a couple of options. Option number 1 is going to be a vector database. Now this is a term that I don't use very often on my channel, but I actually shouldn't have to, because if you've been watching my channel, you should be familiar with geolocation indexes at this point, and vector databases are effectively the same thing. So we basically take our entire coordinate space, as I show over here, we divide it into a bunch of bounding boxes, right? So for example, this top left box, this is bounding box A, this top right box is bounding box B, and then we take each of those bounding boxes and divide them into mini ones. So as you can see over here, we've got AA, AB, AC, AD. And so for a given vector, keep in mind that we're actually continuing to divide these things into bounding boxes, and a given vector's ID within our vector database is actually just going to be like a very tiny bounding box that it belongs to. And the utility of this is that when we actually put all of the names or vector hashes in our database and sort them according to the alphabetical order of those vector hashes, 2 vectors that are very close to one another in the coordinate plane are close to one another on disk, right? So keep in mind this vector over here is definitely going to start with BA, and this vector over here is also going to start with BA. They're close to one another, and so they're close to one another on disk. And so by running a sequential scan from one of those vectors, both above and below it, we can easily find the closest vectors to it. Now keep in mind that the unique thing about a vector database compared to something like a geospatial index is that a vector database generalizes to n dimensions as opposed to just 2 dimensions. But this shouldn't be a problem, right? It's the same exact concept. And if you want to think about this in 3 dimensions, think about like a massive cube filled with a bunch of mini cubes, right? You split that cube into basically 8 different cubes, and then you split those into 8 different cubes, and then you split those into 8 different cubes. And so this generalizes to n dimensions, basically. And so again, the very nice thing is that, let's say I have a given vector. It just takes me logarithmic time to convert it to a coordinate hash. This is all stuff that I go over more so in the spatial index video, and it all pretty much applies here as well. So that's cool. However, there are some problems with this. So vector databases are great, and they make for very good generalizable queries. However, we should keep in mind that this process of actually finding the closest vectors for a given vector is not so simple, right? The first thing we have to do is convert a vector to a geohash, which takes logarithmic time relative to the number of bounding boxes. From there, we have to basically, read all of the surrounding bounding boxes of our vector's bounding box in order to find some of the closest vectors, right? And we basically keep doing this, expanding further and further outwards until we find at least x of them, where x is our threshold of how many neighbors that we need. Then we have to run some sort of Pythagorean distance or Pythagorean theorem to find the distance between our 2 vectors, or some cosine distance or something like that, to basically go ahead and figure out which are the closest, let's say 10 vectors, and then from there we actually have to go ahead and sort our results. So again, we're doing a lot of work here. And then finally, we have to basically return this all to the user, right? So keep in mind that this query that I'm talking about, let's say I have a vector for a new Jordan Has No Life video, and you want to find the 5 most similar entities, because that's how YouTube does it, right? We say return the 5 nearest neighbors for the video that you last watched. Every single user who watches that Jordan Has No Life video is going to be running the same query. So you don't actually have to perform this computation every time, you can just cache it. It's identical for every single user. So for a given entity, every user will be interested in the same X candidate entities, and so we can go ahead and cache it, as I said. Great. So what is this actually going to look like when we cache things? For example, let's say for entity 10, we know that the closest vector is going to be 121, the next closest is 73, or that's the next closest entity, not vector, sorry. And the last closest entity is 67. For entity 16, it goes 3, 55, and 96. So when an entity is first created, we can do 2 things. We can add it to our vector database, because we're going to use the vector database to compute its closest neighbors, and then from there, we find the closest x vectors in that vector database. We can sort them, so we basically run the query that I described in this last slide. We sort them, and then we put them in our index, add them as an index entry. However, there's one thing that's problematic here, right? Let's say that we create a new entity, 18. And 18, it turns out, is actually very close to entity 10, closer, in fact, than entity 67 over here. how is it that we're actually going to go ahead and update our index? We're definitely going to update our vector database, but we also want to be able to propagate that over to our index. And perhaps it's possible that 18 is not just close to vector 10, but it's also close to entity 16. So we have to remove both of these guys and replace them with 18. Well, let's talk about that next. So, upon intersection of a new entity, how can we ensure that it gets cached in the close neighbor list? So let's say we've got this vector b over here, and we just created vector a, which as we can see is pretty close to it over on that coordinate plane. So let's say if we actually re-implemented our neighbor list, instead of making it a sorted list like this, we actually used a max heap, right? So the max heap is saying E has the farthest distance from B. What we could do now is then compare the distance of A to B, which would be this guy here, with E to B, which is that guy over there. So we can see A is clearly closer. So what do? We pop E from our max heap, we insert A, and we let it bubble down, basically. Or actually, I believe when you're inserting in a heap, you insert it at the bottom, and then you let it bubble up to where it has to go. But yeah, that's how things are going to go here. So basically, our final state should look something like this. B now has A and C, which are really close to it, and the furthest vector from it is D, hence why D is at the top of that heap. So one thing to note here is, if we want to be realistic about things, you can't really keep a max heap on a database, right? It's not a structure that works very well over there. You probably do have to keep it in memory, and so this can get expensive. So if you don't want to do it, you're just going to have to incur greater write penalties by keeping this whole thing in a database. If you can do it by storing everything in memory, it'll make the write speed of actually inserting new embeddings into your database quite a bit faster. Next, let's talk about partitioning. So we have two things to partition, right? We have to partition our vector database, and we also have to partition our actual neighbor index that we create on top of that. So our vector database is pretty simple to partition. We've spoken about how we would partition a geospatial index. We want to do the same thing for our vector database. So basically, it's the same exact idea here. We basically want to take any points that are within the same bounding box and squash those on the same partition. Because when I'm running a query and I want to see the nearest vectors to me, it's most useful when all of the vectors that are actually close to me, aka they're in my same bounding box, are on my partition. And what that really means in reality is that it's basically just range-based partitioning on the vector hash. Cool. The next aspect of things is actually going to be our neighbor index. So the first thing that I want to talk about is partitioning it basically the same exact way as the vector database, right? So that, if for a given entity it's very similar to another entity, they're on the same partition. This is going to be useful for us for when we actually insert new entities, right? So if I'm going back over here, let's remind ourselves that, we insert vector A, and it's possible now that that's really, really close to both B and C and D. And so now we want to notice that A is actually going to be in all of their neighbor indexes. So we have to update multiple different vectors at once. If these guys are all on different partitions, that could be pretty slow because now we have to write to multiple different places. We may even have to use a two-phase commit. But if they're on the same partition, we can use a single atomic write to that partition. So it definitely does benefit us to have that. However, at the same time, if that's how we partition things, we may run into problems when actually reading our neighbor index. The reason being, we can have hot partitions. Let's imagine that we're thinking about Mr. Beast videos. They're obviously super popular. Because they're all by Mr. Beast, they're probably pretty similar embeddings. So because of the fact that he individually gets so much traffic, that particular shard that holds all of the Mr. Beast videos would probably get tons of load, and it would be very bad. So what can we do? Well, we can use our typical techniques to try and alleviate load, aka adding more read-only replicas, or adding more caching, or here's another potential solution that I've come up with here, is that we can use change data capture to basically create a second set of read-only replicas of our neighbor index. However, this time instead of partitioning that read-only replica in the same way as our write, basically our leaders, right, which are partitioned by the hash of the vector, now we should basically shard by hash of the entity ID. So this way, if I'm looking at all Mr. Beast entities, they should all be put on completely different shards because we're basically just randomly hashing them out. It doesn't really matter what the video is, we're just going to throw it and try and distribute them evenly. So the way that we would do that is, we've got our neighbor index, which is sharded by the vector hash range on the left over here. And when we write to it, we take all of those changes, we throw them over here into Kafka, into the appropriate Kafka partition based on the entity ID. And then we sync those into our neighbor index, which is actually going to be sharded by the entity hash. And this is what we want the recommendation server to be reading so that we can avoid having a bunch of hot partitions. We can also have a cache in between there as well to speed things up even further, which I do in the final diagram. So yeah, keep in mind that another thing that would be nice is, rather than in this index over here, keeping everything as a heap, we know that it's read-only, so it doesn't really, afford us anything to keep it as a heap. What we could actually do is keep all of those neighbors in a sorted list, because that way we can just return a sorted list back to the recommendation server rather than a heap where, sorting the entries in a heap is still n log n. I digress, but hopefully you guys are following along a little bit here. Cool, so we've gotten through this whole major piece of how we're going to basically find all of the closest neighbors to the last few videos or entities that we've looked at. So now we get into step 2, which is going to be the ranking phase, which is where we start assigning actual scores to our embeddings. So the idea is we want to return a bunch of sorted lists of all of those neighbor vectors, which we're now going to call candidates, right? And now we want to go ahead and merge them together. So let's say we have X different lists, the reason being that we had X different videos that we recently watched, which we're basing this off of, and each of them are length Y, so that means there were Y neighbors in the neighbor index. Our merge time of doing all those things is going to be O of Y log X. This is assuming that we already have the distance of each of these vectors to the actual vector that we recently looked at, right? So for each of these candidate vectors, I know its distance to like the last seen vector that I've looked at in the first place. And so now we're basically merging a bunch of sorted lists, like so. And this requires basically taking a heap of pointers to each of these 3 sorted lists and then cherry picking one element at a time and putting it in our sorted list, like so. And the gist is that is the following time complexity. This is another problem we've talked about plenty on this channel. Cool. So the question now might become, because this is something that people asked me a lot about in the prior video, what if we wanted to actually perform some amount of user-specific scoring per entity, right? Because right now, the way things are built, if I watch a Mr. Beast video and you watch a Mr. Beast video, even if I thumbs upped it and you thumbs downed it, we wouldn't actually assign any different scores to all of these neighbor embeddings that we got back. We would basically treat them the same way. And I imagine that's probably not ideal, right? If I thumbs down a video, I probably don't want to see all of its very similar videos in my recommended list. So what we could do is keep in mind that in addition to basically caching the last few entities that I've interacted with, I can actually cache the interactions that I did with all of those entities, which, for example, for YouTube is basically going to be something like the watch time of that entity, whether or not I liked it or disliked it, and whether I commented, right? These are all pretty good signals, in my opinion, of whether you want to see more of these videos. So what you can do is basically, say, okay, for each of these lists, right? Let's say I watched a Mr. Beast video and now I have 10 neighbors of that video. I disliked the Mr. Beast video. So now what I'm going to do is apply some sort of scaling factor to all of the scores that I have, where the scores are just distances to the Mr. Beast video, on the neighbors of the Mr. Beast video. So maybe because I disliked it, now all the scores go down by a factor of 10, right? So we have some sort of scaling factor, we apply it to each of the lists of Y elements, and that way we can actually keep our read time complexity the same, because now we're still merging a bunch of sorted lists, we just take into account that scaling factor. On the contrary, if you wanted to do a more complicated machine learning inference, right, where we actually went through each of those embeddings and did a customized operation to score each one of them, then what would happen is we would have to resort that entire list globally, and now all of a sudden we would have a time complexity of O of xy log xy, right? Because this is how many candidates we have. We have xy candidates, and then the time complexity of sorting a list is, n log n, so in this case it would be xy log xy. Cool. The next piece that we're going to be talking about is actually filtering out seen entities. Once I have a sorted candidate list, let's say of size 100, maybe I've already seen 10 of those entities and I don't want them recommended to me again. So how can we actually do this? Well, keep in mind we do have some sort of entity history table, right? Every single time that I watch a YouTube video, we're putting that in some sort of database. And we can ensure that we are able to load these things relatively fast by sharding it by our user ID and then basically sorting that or having an index on our entity ID. So that way I can say, oh, if I have entity 10, 14, and 15, has Jordan watched those in the past? I can quickly go to the database and figure that out. So this is pretty good for figuring out whether I've seen a specific list of entities. That being said, it's still a network call, right? And we want to avoid these wherever possible. So how can we avoid this potentially expensive call to the database? Well, we're going to use something that we've used plenty of on this channel as well, and that is going to be the Bloom filter. What is a Bloom filter? Bloom filters are a fixed size memory buffer that are comprised of multiple different hash functions. So you can see I've got 4 different hash functions. So let's say, entity A comes in, right? And I run A through all 4 of those hash functions and it lands A in these 4 buckets. Let's say entity B comes in and B lands in these 4 buckets. Okay, now let's go ahead and say that entity C comes in, right? So I'm considering whether or not I should send entity C as a recommendation to the user. So I take a look at my Bloom filter and I say, okay, maybe C hashes to this bucket, C hashes to this bucket, oh wait, C hashes to this bucket over here. Meaning that we couldn't have seen C before, because if we had seen C before, this bucket would not be empty, right? In reality of just saying A here, we would just have some tick mark like occupied or not occupied. And so because we know that bucket is not occupied, it means that we couldn't have seen C, and so it's good to send it to the user. Now we've avoided an extra database call to figure out whether C was in there. Another thing that we can do, unfortunately, or rather a downside about the Bloom filter, is let's say D comes along, right? So D hashes to this bucket, D hashes to this bucket, D hashes to this bucket, and D hashes to this bucket. You might note that we've never seen D before, but just looking at the Bloom filter, it seems like we have. The point is, if the Bloom filter actually says that we've seen something before, we can't know for sure, and we still have to go to the database. If it says that we haven't seen something before, we do know that for sure actually, and we can go ahead and send that candidate vector over to our client because it's valid to recommend. So again, fixed size memory tells us deterministically when we have not seen an element. If it tells us that we have seen an element, we still have to go to the database. Again, the nice thing about it being fixed size is it means that we don't have to store a ton of data on our recommendation server, right? Because if this is TikTok and I've watched literally a million videos, which at this point on TikTok I've probably watched in like the many thousands of videos because they're so short, you would have to store every single one of those video IDs on your recommendation server, and that's not feasible. So by using a fixed size buffer like this, we can keep the memory footprint relatively low while also eliminating some percentage of calls that we would have to make to the database. Okay, so let's actually continue to talk about Bloom filters in terms of how we would create them. So keep in mind that all of our recommendation servers are already listening to the change data capture of our entity history table. The reason being that for every recommendation, the server has to know my entity history, right? It has to know the last 5 YouTube videos that I've watched. So anything that goes in this table already has to flow through Kafka and into the recommendation server so that we can cache it up here. So in addition to caching those last, say 5 videos, what we can also do is add them into our Bloom filter, right? So we're now going to be handling every single one of these videos. But again, the Bloom filter is a fixed size buffer. And so as a result of that, it's not going to expand beyond our control. We can basically limit it to the size that works best for us. So again, if we're not sure whether we've actually seen the entity, which is going to happen when we have a false positive in the Bloom filter, we're going to have to reach out to the database, the entity history table, to confirm that for us. Okay, now we run into an additional problem, right? Which is that we're basically caching a ton of stuff on our server over here, in particular the Bloom filter, and also ourselves seeing the last few videos. So how can we make this fault tolerant? Because this is all being stored in memory, and if this server gets hit with a hammer and it goes down, well, we're going to lose that state, and that wouldn't be great. So as far as our last few entities that we looked at go, This is pretty easy to retrieve from our entity history database, right? If it's 5 entries, that's not a hard query. I literally just go right here and read them. We can make this a little bit faster by using a local secondary index, right, where we take all of the timestamps of when I actually viewed that entity and we sort them, and that way it's very quick to find the last few, right? So we're going to use a secondary index of view time. However, as far as the bloom filter goes, that is going to be a bit more problematic if we lose it. The reason being that in order to build up that state of the bloom filter, I literally have to keep track of every single entity that I've ever looked at. And so if this guy were to go down, for me to basically restore the state of that bloom filter, now all of a sudden I have to do a full scan of every single thing that I've ever looked at. And so if this is Amazon products or it's TikTok videos, that could literally be in the hundreds of thousands, and that would be very bad. That would be very slow then to bring up a server after it had come down when we're trying to restore this state. So what can we do instead? Well, basically, what we really need is a stateful, fault-tolerant stream consumer. Now at this point, your eyes should be glazing over because you should say, Jordan, you fucking asshole, this is Flink, isn't it? You're close. It's not Flink because Flink is not really meant to be doing HTTP requests, which is what we need to be doing on our recommendation server. However, it is effectively going to do the same exact thing that Flink does, which is every few minutes or every few seconds, what we do is we take this bloom filter, we throw it in S3, and then we also say what index of the Kafka log this corresponded to. So maybe this was S3 at index 172. And so now if this guy goes down and another recommendation server comes up, it loads the data from S3 and then it starts reading from offset 172 onwards in Kafka, and that way it can actually build back up that same exact state. Because if we didn't have the bloom filter, right, if we had an empty bloom filter, we would assume that we haven't actually seen any entities for our user. And if we assume that, then we wouldn't blacklist any of them, and we would just return them entities that they've already seen before, and then they would be upset. So that would be bad. Okay, so we finally made it to the final diagram. I think so far everything I've actually explained okay today, which is in contrast to my normal videos, but of course I will hear from you all in the comments section. So let's go ahead and go through the different paths. Number one, we have the entity upload service. So what would this be? This is, for example, uploading a new YouTube video. So I have it as the same guy, both getting recommendations and uploading entities. In reality, it's probably different people doing this. So you can see here that I basically actually have some in-memory broker. The reason being that it may be a little bit expensive to actually create the embeddings for all of these entities, which is what we have to do when we first create them, right? So if this is YouTube, obviously we've got all sorts of consumers of this list that are, creating different encodings of the video. They're publishing it to a variety of places. They're calculating the thumbnails and different encodings of that thumbnail. But for the sake of our video, I'm just going to draw out this one consumer that I care about, which is going to be the embedding creator, right? So this is some sort of model that we have that maybe gets updated every once in a while. But for now, all it's going to do is basically take our video and convert it to a vector. And from there, we have to do a few different things with that vector. For starters, we have to put it in the vector database, which is sharded on our vector hashes, as we discussed, so that way you get good data locality to find similar vectors to the one that we just created. From there, we now say, okay, for the new vector that I just created, I just found the 10 closest neighbors. Let me now look at those 10 closest neighbors in our actual neighbor index and see if I have to update those neighbor indexes to reflect the fact that I now have a new vector. So we can go ahead and do that. We would put that in our neighbor index like so, and then in order to achieve fault tolerance on this memory-based cache, what we do is we take all of the changes that we make, we throw them in Kafka, we basically reshuffle them because they were previously sharded on vector hashes, and what we really want for fast reads and making sure that we don't have any hot partitions is to partition these guys on the entity hash range, right? So I don't care about the vector hash as far as partitioning. I want basically, video 10 might be represented as, video 10 might be represented as a vector of like 3, 47, 62. This is the vector. But instead of sharding on this, now I want to shard on this. Cool. So we're going to shard on this guy instead so that they're evenly distributed across all entities across this table over here. In addition to updating our neighbor index, as I mentioned, so that this way we can make sure that new videos are included in recommendations, we also actually want to put the mapping from 10 to its particular vector into the entity database over here, we can just index these by the entity ID and shard them accordingly. The reasoning being that for a given entity ID, I would like to be able to very quickly find its embedding, and so we need an index to do that. Great. We have all of that. So we've got our neighbor index, right, that we care about basically, being able to quickly figure out all the neighbors for a given video that I've watched. We've got some cache because, let's say for Mr. Beast videos, tons of people are going to be getting that in their recommendations. And so videos like those should be hitting this neighbor index cache. And then, of course, the next step of this process is actually going to be interacting with entities, right? A new video gets posted, I watch it. So what types of things go in here? Maybe likes, comments, watch time. And that's all basically going to flow through our entity history database. So this is keeping track of all the user interactions with the videos or the Amazon products or anything like that they interact with on our service. Again, we want to shard those by user ID so that it's very easy to load for a given user. We want to index these by entity ID so we can quickly tell for a given entity whether I've interacted with it or not. And again, it would also be nice to have a secondary index on the timestamp of all of those interactions so I can very quickly figure out what the last few interactions that I performed actually were so that we can formulate recommendations based off of those. Again, in typical Jordan fashion, we're going to have these flow all through change data capture and into Kafka, and then we're going to cache them on our recommendation service. The reason for this being the recommendation service is saying, hey, for user 55, the last entities that they watched were 12, 13, and 62, right? These are the last 3 entities that we watched. So now, when user 55 over here goes and asks for some recommendations, this recommendation service is going to say, ooh, hey, for 12, 13, and 62, go get me the closest entities to that. It's actually going to reach out into the neighbor index cache, which if it's not populated, will reach back to the neighbor index. It's going to figure out all of those closest entities, and then now on here on this recommendation service, we're going to perform sorting, which again, we're going to use basically a heap and all of these sorted lists, merge them together, and then return them right back to the user. Note that this really only works, all of this pre-computation and all of this pre-caching, if we're sure that deterministically a given recommendation server is going to be handling all of these requests for a given user. And the way that we do that is by basically sharding all of them on the hash of the user ID. So we're vertically scaling out via a load balancer, or sorry, not vertically scaling, we're horizontally sharding or horizontally scaling out this recommendation service based on the hash of our user ID. And we're going to use consistent hashing to do that. Somewhere over here we would probably have some zookeeper, blah, blah, blah. So another thing to note, or to remember, is that the recommendation service is also holding our Bloom filters. And we don't want to lose those Bloom filters. We need these guys because it's going to help us avoid extra calls over here to our entity history database. So as long as we have this Bloom filter, it's a pretty nice optimization, but it's very easy for this guy to go down and lose the Bloom filter. So that's why every few seconds we go ahead and checkpoint our state of the Bloom filter over here in S3 as well as our Kafka offset, and that way if we have to bring up another node and basically have it restore the state of this previous recommendation server, we can relatively quickly do that by reading from S3, reading from the corresponding offset in Kafka, and then quickly going to our entity history database and getting the last 3 videos that that person has watched. Now all of a sudden we have restored all of our state. Well guys, I hope this makes sense and I hope it was a good one. Again, sorry about the ads. I'll see how the feedback is on it, but I tried to make it somewhat entertaining. And yeah, I'll see you guys in the next one.